Hey, just wanted to do a very quick kind of like, not even a wrap up, just like tying up some loose ends from chapter 2, unit 2, excuse me. So some like last minute reminders. Remember we talked about extrapolation, so we want to make a prediction. It's the whole point in what we do. Everything in unit 3 is about like scatter plots and correlation. And the reason we look at scatter plots, the reason we think about correlation is so we can make a prediction in like the y direction. And we want to be able to make predictions, but remember, when we extrapolate like too far out from the domain of the x values that we actually have collected data on, it can be dangerous. We don't know if the pattern's going to continue or if it's going to change, right? So we should make a note of that if we're asked to do that. We talked about outliers. When we talk about outliers, we're talking about like in the y direction, like a point that has like a bigger than typical residual value when I compare it to like the other points. Whereas the high leverage points are, there's like a big gap in the x direction, either like on the low side or the high side. And they may follow the pattern and might just be high leverage points, or they might be high leverage points and outliers, right? So like, for example, if I have my scatter plot looks like this point here is high leverage and it follows the pattern. This point is a high leverage and an outlier because it doesn't follow the pattern, but there's this like gap in the x direction, right? Influential points are any points that could change, the line itself, the least squares regression line itself. So like the slope, the y-intercept, it could change the R value. It could strengthen the R value. Like in the case of that point, it can weaken the R value. And influential points tend to pull the regression line towards them. So you may not be able to, if you look at a residual plot, you may not be able to identify the influential point as much as you would be able to, or as clearly, I should say, or as easily as you would be able to on like the regular scatter plot. Remember, we looked at some examples in class of like when I have like scatter plot that looks like this, and then I have like this influential point. Instead of the LSRL really should be kind of like in the middle, right? And that's probably not like the greatest line of all time, but I'm trying to switch colors and this is being very uncooperative. So I'm not going to switch colors. But anyway, so that would be like maybe my LSRL without the outlier, and then with the outlier, remember we had that line that like it moved all the way up. So like when I look at the residual plot, think about it, is going to look like all these points below and then this one, just that one above, right? It's not going to be kind of as obvious. So a lot of times on residual plots, it's harder to identify those influential points. All right, this last bullet point, let me clarify what this kind of means here. So if I look at like age versus average height, so what I'm talking about is averages. So like, for example, let's say like males, right? And like this is their age, males at age like let's say like 2, 3, 4, 5, and 6 or something like that. And if I were to say average height, so like the average height of males, right? There's going to be a really strong, possibly linear, but maybe even nonlinear relationship between these things, these two variables, the age and the average height. It's like, if it's the average height, you're only going to have one average height value for each age, as opposed to if I look at age and like individual heights. So like age 2, 3, 4, 5, 6, whatever, right? If I look at individual heights, people who are 2 years old, males who are 2 years old, I'm going to have some variability in their heights. I'm going to have some variability in the 3-year-old heights, some variability in the 4-year-old heights, some variability in the 5-year-old heights, right? So I might still have like that same linear positive relationship here, but it's going to appear to be much stronger if I look at average height than as if I were to look at individual heights of like the individual males. So we typically shouldn't look at like things like age versus average height, age versus average weight, things like that, because the fact that we're taking an average on this one X value, it's an average. It's like putting us in the middle. So, okay. Last but not least, confounding variables. And we've kind of referred to these a couple times. It's a variable that it's not a variable that we chose to study. So it's not the explanatory, like the X or the response Y variable that I've chosen to look at in this specific study, but it has some influence over the relationship between the X and Y that I did choose. For a perfect example would be the silly example that we've looked at a couple times, like the income that the ski resorts have made versus like the number of deaths due to tangled bed sheets, right? So there's not an explanatory response relationship. Like we don't think one necessarily causes the other to change, but there was a strong relationship. Remember we said like there was that pretty strong relationship when I looked at those two things, and we talked about why would that be. A big confounding variable would be just like the population in that area. More people, more income, more tangled bed sheets, right? So it's like that third variable is really the cause of what's changing, like both of these things to increase at the same time. Maybe another example might be like the amount of people at the beach and the number of ice cream cones sold, right? Like the more people at the beach, I would think the more ice cream cones are sold. But in addition, probably the more important variable is like the temperature or the season, right? The weather essentially is going to probably be a better predictor of like how many ice cream cones are sold and how many people are at the beach. But even when I take that variable out, the weather, I still see like probably a strong positive relationship between those two things. In almost every situation, you can come up with at least 1 or 2 or 3 confounding variables, and you might be asked to do that. So like, for example, you could look at something like IQ and reading ability in like elementary kids or middle school kids or even high school kids. So like IQ versus reading ability, you would think typically that as IQ goes up, the reading ability also goes up, which probably is true. They probably have a positive correlation and relationship. But, and the IQ it is probably an explanatory. Let me draw this out. So I probably do have like an explanatory response relationship to some extent, right? My IQ going up or a person's IQ going up probably has an influence or causes to some extent the reading score to go up as well. But what else could be at work here? Like what else is causing the reading score to increase? A lot of times like parents, education levels, socioeconomic status, things like that, whether or not they went to like a preschool or like a pre-K, I should say, right? So like all of those things could have an impact as well. Attendance at school even. So those are the confounding variables. And remember when we talked about like R squared is like what percent of the variability in the reading score is because of the IQ. In other words, as the IQ is going up, the reading score is also going up. It tends to go up, but is the reading score going up directly as a result as a result from the IQ going up? Well, the R squared tells you like what percent of the variability in the reading score the IQ can be like attributed to. Well, those other confounding variables is the leftover percent. So like if my R squared is like 90%, let's just say, for example, so I would say like 90% of the variability in reading scores is due to the linear relationship between IQ and reading score. Well, what about the other 10%? That would be like the socioeconomic status, the schooling, parents' schooling, all that other stuff. All right. Nothing too crazy here though. Like it doesn't really get too crazy. Like in different situations, you might be asked like, give me a confounding variable. And in almost every situation, you should be able to think of like at least one thing that could affect Y other than the X that you're given. Okay, that's really it. Just a reminder, here's some review that you could be working on. This is posted, the answer key is posted in the folder from last week. Originally, I told you to skip part of number 1. Now you can finish up that whole thing. And also keep in mind your Unit 2 test is not really on all of Unit 2, right? We're skipping A. Well, we already tested on A. And the second half of D, we're going to hold off on. So notice like the Unit 2 review, I always tell you to do that like end of unit review as a practice test. Really, you can't do like all of it. So just those problems there. Let me know if you have any questions. Thanks.